So today we'll start with chapter 10. After we're done with chapter 8, we'll move to chapter 10, which is all about vectors and the geometry of space. We'll be covering all sections, all from 10.1 till 10.6. We'll cover today 10.1 and 10.2. In 10.1 and 10.2, we're just introducing the idea of vectors in the plane, in the two-dimensional space, and in the space, in the three-dimensional space. This is a bit similar to what you have covered before in physics. So you've heard about vectors before, in math in your previous studying. So in 10.1, we're covering vectors in the plane, just basic knowledge about vectors. So when we talk about vectors, we mean that directed line segment, which is extended from one point P, which we use it as an initial point, towards Q, which is the terminal point. And as you see here, just how do we use, or how do we write the vector? We say from P to Q. So we write P before Q, PQ, and this arrow shows the direction that we're moving from P to Q. And this vector, clearly that it has a direction. So this is a directed line segment. The length of this vector, this is what we call the magnitude of this vector, okay? So the length of this vector, this is what we call the magnitude of this vector. And we use this notation to show that this is the magnitude. It's just like two vertical lines. And in between it's PQ, and the arrow on top, it goes from P to Q. So this is what we use to represent the magnitude of the vector. Notice any vector is special by what? Two things. The magnitude, its magnitude, and its direction. This is what makes any vector unique. So it has its magnitude and its direction. Remember, the magnitude, we mean the length of that vector. Okay? Now, when do we say that any two vectors are equivalent to each other? You see just this word, equivalent to each other. It means that they are equals to each other. So again, we said what makes any vector unique is its magnitude and direction. So any two vectors are equivalent to each other if they have the same magnitude and the same direction, which makes sense. So look at these three vectors, A, B, C. All of them, they have the same direction, same length. So these three, we call them equivalent vectors, equals to each other. So A equals to B equals to C. The only difference here is just their location in the XY coordinate. Just where their location, where's their initial point. Now, dealing with vectors, sometimes we need just to make the vector like larger, smaller, change the direction. So we need to multiply with a constant. And at this time, when we deal with vectors, we don't say it's a constant, we call it scalar. Okay, we'll call any constant we multiply by the vector, we call it scalar. So the scalars are the constant we multiply by the vectors. So we need always to be careful how to distinguish between vectors, okay, and scalars. Scalars for us, it's just like only a constant, so it has no direction. Now, how do we add two vectors? I'm sure just you covered this before, dealing with forces in physics, many other applications. You needed to add two vectors, and in order to find the resultant of their total, their summation. Okay, so you cover this mainly you need it more in physics. So for scalar multiplication, it's just like I'm multiplying by a scalar, by a constant. So that constant either makes the vector like larger. If it's more than one, let's say that we start with the blue one, u. If I multiply by 3, so this is 3 times taller than u. If I'm multiplying by half u, so this is half the length of u. Notice here, this scalar is what? -2. So I'm doubling the size and opposite direction. So the function of the negative sign is opposite direction, okay? So how do we say control the sign? It's just by, the direction is just by the sign. Positive, it's the same direction. Negative, I flip the vector. It's the opposite direction. Now, for the position vector, we said just if you saw here, in this example, we saw that the three vectors are equivalent to each other, but they have this different locations. Now, just to have something in common that everyone agrees that this is the standard position for the vector, they agree just to have the standard position, just something like A. So they fixed the initial point at the origin of the xy coordinate, and the terminal point will be moving freely along the whole xy coordinates, the 4 regions. So the standard position is just like this. So we fix the initial point at the origin. So for the standard position, we have it just to start from the origin, and this is the terminal point. If I look at the points as order pair, so this point is the order pair A1, A2. This vector, I can use this notation. Notice this is order pair, just only like any normal point. So this is a point. And here this is a vector. You see the notation for the vector, we use the vector A, we use it as A1, A2. They use these two brackets to represent vectors. So this is the vector A, A1, A2. Now what's this A1, what's this A2? The first one is what we call the first component, and the second one is the second component. So if we try just to represent that in the xy coordinate, the blue vector is in the standard position, which we call the position vector. Notice this height, the vertical height is A2, the horizontal is A1, so this distance is A1. We add the absolute value because we need it as a length, and this is A2. So this is what makes that vector as a first component, second component. Notice every time, if we need just to represent a vector, we need to use this type of brackets, okay? We need to use this type of bracket. Okay, let's see next, what do we have? Now we said just we need to find the length of that vector, okay? We need to find the length of the vector. How do we find the length of the vector? If you look at this triangle that we created, if I try to find the length of this hypotenuse, look, for this triangle, this is a right triangle. So the vector here, the magnitude of the vector is same like the length of the hypotenuse, which we can use Pythagorean identity. So this is basically, if I need to find the length for A, which is the magnitude for A, the vector A, so it should be the square root of A1 squared, the first component squared, plus the second component squared. So first component squared plus the second one squared. So now if I need to find the magnitude for any vector, I do square root, first component squared plus second component squared, okay? When do we say that two vectors are equal to each other? Let's say that this vector, A1, A2, B is B1, B2, they are equal to each other when, if the first component equals the first component, and the second component equals to the second component. This is where we can say that they are equal to each other. So you just compare them, first with first, second with second. Now, just we need some operations with vectors. How can we add vectors, subtract, multiplication, basically scalar multiplication. So for addition again, just like as expected, if I need to add two vectors, I'll add the first component with the first. So A1 plus B1. And the second one, second component with the second component. Same thing for subtraction. First minus first, second minus second. Scalar multiplication, just like you're using distributive property. So I'll multiply C by A1 and A2. Now what I need you just to be careful about, just when we deal with all of these three operations, that we started with two vectors, okay? And the result is new vector, another vector. So if I'm adding two vectors, subtracting two vectors, scalar multiplication, the result will be what? Another vector. Okay, so we'll get another vector. Here they are showing you that if there's a constant inside the magnitude, I can take it out, but I have to add the absolute value. Remember, anything like length, magnitude, it should be always positive. We can't deal with negative. this is very simple question about the arithmetic of vectors. So if I have the vector A as 2, 1, vector B as 3, negative 2, I need to find A plus B. Okay, let's see. We need to find what's A plus B. So this is equals to, what's A? The vector A is 2, 1, plus the vector B is 3, negative 2. Now adding them, so what you'll get, 2 plus 3 is 5. 1 plus negative 2 is negative 1. Notice that their addition is another vector. Now, part B, what do we have in part B? We have scalar multiplication. I'm just multiplying A by 2. You're just multiplying A by 2. And this is equals to 2 times the vector A, which is again 2, 1. Just like you think about it as using distributive property. So 2 times 2 is 4. 1 times 2 is 2. Now this vector, what do we know about this vector? It has the same direction as A, okay? So scalar multiplication doesn't change the direction if it's positive. So it has the same direction as A, but double the length, okay? So let's move to C. C here, just we're making just more. We're dealing with scalar multiplication and addition. So what do we need to do for part C? I'll do 2A plus 3B. And this is equals to 2A. We can use what we have from B. So 2A is just, let's do it. So 2 times A, it's 2 times 1 plus 3 times B. 3, negative 2. Again, we'll use distributive property. So this is 4, 2 plus 9, negative 6. Now we add them, and this is equals to 4 plus 9, 13, 2 plus negative 6, negative 4. Again, the result is what? Another vector. The result is another vector. So dealing with vector arithmetic, just like straightforward, very easy. Okay, now see this question. They give us again two vectors, okay? Vector A, 2, 1, B, 3, negative 2. And we need to find, this is same question, okay? Here we did A, B, C, and this is here D and E. For D, we need to do subtraction, 2A minus 3B, okay? Same technique, we're doing the same thing. So D is 2A minus 3B. Let's do it fast. So 2A, look at A times 2. So this is 4, 2 minus 3 times B. 3 times B, which is 9 minus 6. Subtract them. 4 minus 9 is negative 5. 2 minus minus 6. Careful if you have double negative, so it's positive again. So 2 plus 6 is 8. So this is what we have in part D. Now part E, if you see part E, we need the magnitude of the vector in part D. So whatever we have from part D, we need to find its magnitude. So this is the magnitude of 2A minus 3B, which is equals to the radical of, see, this is the vector. So it's negative 5 squared plus 8 squared, and this is equal square root of 25 plus 64, and this is equal square root of 89, and this is the magnitude of 2A minus 3B. Okay, so all the arithmetic are really simple. Okay, there's more properties for the vectors. There's something what we call the zero vector, okay? So this is what we call zero vector. So zero vector, as expected, it's a zero. Notation is 0 in bold, and it's a vector where its first component and second component are 0, 0. Okay, so this is a vector with length of 0. So it's just only like a point. So it has the length of 0. Now, if I need just to think, what can we add to the vector to cancel it out? Just like remember with numbers. So if you have 3 and you need to add something to make it 0 again. This value that we added, usually we call it the additive inverse. Okay, what cancel the 3? Usually we add what? -3, which makes it 0. This is what we call the additive inverse. So for any vector A, the additive inverse is -a. Just only basically to multiply by -1. So my -1 distributes, so it's -a1, -a2. What's the magnitude for these vectors? For A and -a, they have the same magnitude for sure. Just opposite direction, but they have the same length. So the magnitude of -a is exactly the same like the magnitude of A. But if I add them, A minus A, so if I'm adding the vector A minus the vector A, so the result will be what? The 0 vector. The result will be the 0 vector. Now, this is important part. This definition is saying what? It's showing when can we say that two vectors are parallel to each other? Remember, in general, when we talk about parallel lines, we mean that these two lines, they have the same slope, okay? And they will never meet. If you extend them like forever, they will never meet. You remember that this is the meaning of two parallel lines. So they'll never meet. I have two lines that they will never meet. Okay, how can we see that with vectors? When do we say that two vectors are parallel to each other? So two vectors are parallel to each other. We're talking for sure about non-zero vectors. So they are parallel to each other if and only if I'm able to write one of them as the scalar multiple of the other. So A is parallel to B if B can be written as CA, where C is a scalar, okay? This C is scalar. And A and B are the vectors. I just prefer usually just to use the arrow on top of them. So you distinguish, this is a vector and this is, if you can't just easily show that this is bold, so it's easier to use the arrow on top. So this C is scalar. So I can say that they are parallel to each other if B is written as, or can be written as C times A, scalar multiple of A. Okay, how can we prove that? One way we can do it, see this question. It says determine whether the given pair of vectors is parallel. Okay, I need to see that they are parallel to each other. So what do we mean by parallel vectors? I mean that B can be written as C times A. Let's again use the arrows. So it's scalar multiple of A. Okay, let's see. Let's double check. So if A can be written as CA, how can we prove that they are parallel to each other? So the way of proving that, we can do it by this way. So I'll say that let's say that A is equal to 2, 3. B is supposed to be C times A. B is C times A. So B is equal to what? C times A. So it's 2C, 3C. Now, this is A, this is B equals CA. This is supposed to be B. Now compare this to B, the given one B. I'll compare it to this B. How can I do that? Basically what I'm doing is this. I'll say that since this is B and this is B, so they are equals to each other. These two are B. Okay, so both of them are B, so they are equals to each other. So the first component is equal to the first component. Solve for C. So this implies that C is equal to 2. Okay, good. I'll do the same for the second component. So 5 is equal to 3C. solve for c. So c is equal to 5 over 3. And this is a contradiction. This is supposed to be the same c. So if I'm getting different c's, so they are not parallel to each other. So this is one way. This is like the long way to do it. They do what? They start with A. They say, assume that B is equal to CA. So they come to A, they multiply it by C, and then they make B equals to each other. This B with this B. First component equals the first, second equals the second. And they check what's C. If you get different C's, so they are not parallel to each other, so, which is a contradiction. It's supposed to be the same C. If you have the same C, yes, they are parallel to each other. So this is one way. For me, I prefer that you do it this way, much easier. So if you have any two vectors, let's say A equals A1, A2, and B is equal to B1, B2. If I need to check that they are parallel to each other, what I'm going to do, just take the ratios for the first component. So B1 divided by A1, is it equal to B2 divided by A2? If they, which is C, basically, what I'm doing is just like C. So if they are equals to each other, yes, they are parallel. If not, they are not parallel. So I can do it just very fast. So if I go back to the same equation, part A, so I'll say, okay, 4 over 2, is it equal to 5 over 3? It's not. So they are not parallel. You see, it's very fast. Now looking at the second question, I'll use my technique, this one. So I'll take first component divided by first, second divided by second. So I'll check negative 4 divided by 2. Is it equal to negative 6 divided by 3? Notice both of them equals to negative 2, which is correct. So that means they are parallel line. They are parallel line. It's correct. They are parallel lines. Okay. If you use the method for C, you do the same thing. So I'll say like 2 equals, or 2C. If I use the idea of C, I'll say 2C equals to negative 4. 3C equals negative 6. Solve them, you'll get C equals to negative 2, which is correct. In both equations, you'll get C equals to negative 2. So whatever you like, you can use the idea of C or this ratios. It's up to you in the end. Okay, now this theorem is just like basic. We saw this before, even with dealing with real numbers. So they have almost the same properties like the real numbers, but these are vectors. So if I'm having 3 vectors as A, B, and C, in V2, I mean in the 2-dimensional space, and we have a scalar D and E. Notice usually they write the vectors in bold. The scalar, they are not bold. The scalar in the real numbers. So if I add the 2 vectors, so A plus B is equal to B plus A, which is the commutative property. This is the associative property. So if I'm adding 3 vectors, it's up to you. Either you add the first 2 or you add the last 2. They are the same. If you're adding a 0 vector to any vector, you'll get what? The same vector. 0 vector, change nothing for the addition. A minus A plus negative A is the 0 vector. If you have a scalar and you need to multiply it by A plus B, so just like you're using distributive property. So dA plus dB. Same thing here. I have a vector and 2 constant. Now if I'm multiplying by 1, so A times 1, it's still A. A times 0 vector, it's 0 vector. So you see these properties exactly what you know from real numbers. So it's similar, okay? But these are vectors. Now, in the 2-dimensional space, sometimes they give us the vector ready like this. You have the vector in this notation, x, y. But what if we have the vector? We don't have the vector, but we have the 2 points. It's not a position vector. Remember, what do we mean by position vector? It's in the standard form. So the initial point is 0, 0. Okay, this is the position vector. Sometimes we're not that lucky. We don't have the vector as a standard position vector. They have it anywhere in the xy coordinate. So we know the initial point, we know the terminal point. So if we were given 2 points, initial point, terminal point. And we need to find the vector. Okay, we need to find the vector from A to B. This is the vector AB. So what I'll be doing, very simple. I'll use these 2 points and I'll subtract. I'll take delta x, delta y. This is the vector. Okay, so you're subtracting delta x, delta y. Remember, anything we say delta, that means it's the change. So I'll use x2, delta x, delta x, delta y. And try always to follow the vector. It's given as AB, so I need to subtract B minus A, okay? So if always the vector is just AB, that means you need to subtract the point B minus the point A, okay? Always terminal minus initial. So the terminal point minus initial point. So see this example. We need to find the vector with initial point at A 2, 3 and the terminal point B 3, negative 1. So basically what I'm finding is this vector A, B. You see? A is the initial point, B is the terminal point. Now this stands for x1, okay? So this is x1, y1. This is x2, y2. So if I need to find the vector, we'll use the notation for the vector. So it's x2 minus x1. So this is a 3 minus 2. y2 minus y1. So it's negative 1 minus a 3. And this is equals to 1, negative 4. And this is what we get here is a position vector. Remember what we have here is a position vector. So just be careful. What's the initial point? Terminal point. We always do terminal minus initial, okay? Terminal minus initial. Delta x, delta y. Okay, let's move next. You see here the graph for these vectors that we already found. So this is the initial point, terminal point. This is 2, 3, 3, negative 1 in blue. And then what we found here as a position vector, it's in the standard position. So this is the initial point, now 0, 0. And the terminal point is what we have as 1, negative 4. So just like we moved it to the standard position, delta x, delta y. Now, there's just like when we deal with finding or representing the length, the weight, the height, there's usually more than one unit that we're using, okay? So same thing, like as you have centimeter and you have inch, as you have pound and kilogram, same thing with vectors. There's another way to represent vectors, not only by this form. So this is the form that we covered already. We say that this is A1, A2, and we used these two types of brackets. This is first component, second component. There's another nice form that they use it a lot. You saw it a lot in physics, which we call the standard basis vectors. They use the I and J to represent vectors. So what are these standard basis vectors? The standard basis vectors are basically vectors in the a horizontal vector and a vertical vector, where on the x-axis, this one, I, its initial point is 0, terminal point is 1, 0. This is the standard basis I. Notice that the vector, if I need to write it, so it's 1, 0. And J is the vertical one, so J will be 0, 1. The length for this vector, clearly, the magnitude or the length is 1. So this is what they call a unit vector, okay? So it's a unit vector. Both of them, I and J, they have the same length. Now, there's a way just to represent the same vector A as A1, A2. Sorry, we can easily write it as A1I plus A2J. A1I plus A2J. If we need to check this out, see, this is A1. What's I? We said I is 1, 0. If I need to add it to A2J, J is 0, 1. Just some arithmetic, add these two, you'll get again A1, A2. This is 1. Okay, so it's another way to write any vector. So now, instead of saying just the vector is only like A1, A2, I can use the standard basis, which is A1I plus A2J. Remember always, I stands for the first component, the horizontal unit vector. And J, for the second component, we use the vertical unit vector, I and J. Okay, this is what we proved already. Now, we said that I and J are unit vectors and their length is 1. Now, what we'll be doing here in this theorem, which is really useful, they'll do what? They'll come to any vector, okay? If we have any position vector A, which is A1, A2, and we're trying to get a unit vector, okay? We try, just let's say that you have any vector, any length. We need to get a unit vector out of this vector. We'll take only a vector, same direction, but with length of 1. Okay, it's just like imagine it that you're taking a part of this vector with the same direction, but the length is only 1. The length is only 1. How do we do that? It's easy way. I just see the full vector A and I divide it by its magnitude. If you divide any vector by its magnitude, you always get a unit vector, which we'll call U. Okay, so this stands for unit vector. So remember always, if you divide any vector by its magnitude, you'll get what? A unit vector. This process, we call it normalization for the vector. Okay, so if we're doing normalization for the vector, we mean we make its length 1. Okay, so we divide the vector by its magnitude. We're dividing the vector by its magnitude. This process, we call it normalization. Okay, see the next question. What do we need to do? See, this is example 1.4. It tells us to find a unit vector in the same direction as A. Okay, easy. Same direction, but the length is 1. How can we get this? We know from the previous slide that always I can get the unit vector U as A divided by its magnitude. Very good. So clearly I need to find the magnitude first. So I know what's A. It's given already in the question. It's a 3, -4. The magnitude for A, remember we find it as what? Square root. First component squared plus second component squared. And this is equals to 9 plus 16, 25, which is equals to 5. So now the magnitude is 5 and this is the vector. Okay, let's find U. So U is equal to A divided by its magnitude. And this is equals, what's A? 3, -4. Divided by, the magnitude is basically a scalar. So divided by 5, so a scalar will distribute the scalar. So this is 3 over 5, -4 over 5. So this is a unit vector, okay, with the same direction as A, and its magnitude is 1 only. Its magnitude is 1. You can check. Try to calculate the magnitude for this vector. It will be equal to 1. So in general, if I need to take one part of the vector, just only a unit vector, the length of 1, with the same direction. So you divide the vector by its magnitude. Remember, the magnitude is a scalar. So when you divide, you distribute, just like you're multiplying by 1 over 5. Okay. What else do we have? Okay, so by this example, we'll finish section 10.1. That's all about 10.1.